Imagine you just pull out your phone, right? And you type, hey, find me a fast, cheap flight to Tokyo.
Oh, a classic request. We do it all the time.
Exactly. And in like 3 seconds, your AI assistant replies with a $300 ticket, which sounds amazing.
Until you look at the actual details.
Right, because it features this brutal 14-hour overnight layover in some airport you have literally never heard of.
Yeah, which totally ignores the fast part of your prompt.
So you reply, and you say, no, I said fast, direct flights only.
And this is where things usually go off the rails.
Completely. The AI thinks for a second, and then it just spits back an identical 14-hour layover flight that costs $295.
You just dug its heels in on the word cheap.
Right. So you try a third time, you say, stop giving me layovers, and the AI stubbornly offers you a third variation of that exact same terrible, slow flight.
It is incredibly frustrating.
It really is. And it makes you wonder, why is the most sophisticated trillion-dollar technology on Earth suddenly acting like a brick wall?
Well, it creates this bizarre illusion, right? Because the model clearly understands the English language perfectly fine.
Yeah, it speaks perfectly.
But it completely lacks the cognitive flexibility to understand a changing situation. It locks onto your first instruction cheap, and it just refuses to let it go.
And that stubbornness, that exact phenomenon, is our entire mission today.
Yeah.
Welcome to the Deep Dive.
Glad to be here.
We are exploring why our current incredibly advanced AIs act like what researchers are now calling static parrots.
Such a great term for it, honestly.
It really is. And more importantly, we are looking at how a brand new breakthrough from Google research is fundamentally rewriting that architecture.
Yeah, this is a massive shift in how these models actually think.
We are pulling from a stack of fresh sources today, specifically a landmark January 2026 paper from Nature Communications.
That's DOI 10.11038 S41467-025679986 for anyone keeping track.
Thank you for that. And we are looking at that alongside a major technical update from the official Google research blog from March 2026.
So we are looking at the mechanical leap from an AI that just recognizes static text patterns to an AI that actually, evolves its understanding in real time.
Like it actually learns while you are talking to it.
Exactly. We are talking about teaching language models how to deduce clues like a human detective without needing to be reprogrammed in the cloud.
So by the end of this deep dive, you are going to understand a completely new paradigm in artificial intelligence.
It's going to change how you interact with your devices, for sure.
Let's start with the problem itself. We know the current heavy hitters models like Gemini 1.5 Pro or GPT-4o are phenomenal at certain tasks.
Oh, absolutely world class.
So why do they fail so spectacularly at multi-turn reasoning? Why do they get stuck in that awful flight booking loop?
It comes down to a really fundamental limitation in how transformer architecture handles probability.
Okay, break that down for us.
So current large language models are, at their core, just engines designed to predict the next best word based on vast amounts of static training data.
Right, the autocomplete on steroids analogy.
Exactly. When you ask for a cheap flight, the model activates this dense web of statistical weights related to low prices. It makes a very strong initial guess.
But then I correct it. I tell it I want a fast flight instead.
And that is the problem. As you continue talking, as you give it corrective feedback, the model lacks a native mathematical mechanism to dynamically update those internal weights.
But wait, I have to push back on that.
Go for it.
When I am chatting with these major models, the interface shows me the whole conversation. The model has the chat history, right?
It does, yes, the context window.
Right. It can literally read the text where I just said, I want a fast flight. If the text is right there in its memory, why isn't its internal belief about my preference changing?
Because reading a chat history is not the same thing as mathematically updating a belief system.
Oh, interesting. What is the difference mechanically?
When an LLM reads your chat history, it is just looking at a longer, flat string of text and trying to predict the next token that fits the overall pattern.
So it's not actually weighing the importance of the new information.
No, it anchors heavily to the early tokens in the conversation. It doesn't possess a mechanism to say, hey, the user just complained about layovers, so I need to run a calculation to lower the probabilistic weight I am giving to price.
And increase the weight given to speed.
Exactly. Text pattern recognition is flat. Belief updating requires a dynamic, probabilistic calculation.
Okay, let me try to unpack this with an analogy. It is like having a friend who hears you say you want a burger for lunch.
Okay, I am with you.
You get in the car and clarify, actually, I am a vegetarian now.
Pretty major update to the prompt.
Right. And instead of fundamentally updating their mental model of your dietary requirements, they just process the new sentence as an add-on.
Oh, I see where you're going.
They say, oh, my bad. Here is a coupon for a cheaper meat burger. They heard the new words, but their internal premise didn't shift at all.
That captures the mechanical failure perfectly. The AI clings to the prior assumption and completely fails to integrate the new evidence.
It is maddening. And the Nature Communications paper actually quantified this failure, didn't they?
They did. The researchers found that after the very first interaction, traditional AI models essentially hit a brick wall.
Just totally stall out.
Yeah. Without specialized training, their accuracy in tracking user preferences over multiple rounds of conversation stagnates at about 38%.
A 38% success rate is abysmal for a system that can pass the bar exam.
It plateaus completely. I mean, you can argue with the AI for 10 more rounds, and it will barely budge past that 38% mark.
Because you are trying to force a static pattern matcher to do dynamic reasoning.
Precisely. It just wasn't built for it.
Which brings us to how Google solved this. And the really fascinating thing is, they didn't invent some wild new neural network architecture from scratch.
No, they didn't. They actually reached way back into the 18th century.
Yes, we are talking about Reverend Thomas Bayes.
Thomas Bayes was an 18th century statistician and minister.
A very cool combination of jobs, by the way.
Right. And he formulated a mathematical rule that has become the absolute foundation of how rational systems should update their beliefs when faced with new information.
And we call that Bayesian inference.
Exactly. Bayesian inference.
The classic textbook explanation for this is always a murder mystery. Like, the detective thinks the butler did it, but then finds the gardener's muddy boots and updates the odds.
That is the standard example, yeah.
But to put this in a modern technological context for you listening, it feels a lot more like a GPS system.
Oh, that is a great way to look at it.
When you start your drive, your GPS has an initial belief about the fastest route. Statisticians call that the prior.
The baseline assumption.
Right. But halfway there, the GPS receives satellite data about a massive traffic jam ahead. That is the new evidence.
And it has to react to that evidence.
Exactly. The GPS doesn't just stubbornly keep you on the highway. It takes the prior, factors in the new evidence, and calculates a brand new, updated route.
And that new route is what we call the posterior.
A continuous probabilistic update.
It is a highly accurate comparison. Google Research wanted to see if they could teach modern LLMs to natively perform this kind of continuous Bayesian math internally.
Purely through the flow of a normal text conversation.
Yes. And they created a training methodology called Bayesian teaching to pull this off.
The sources outline that they used supervised fine-tuning to achieve this. And they didn't just test a single proprietary Google model.
No, they applied this to several major open weights models, specifically Gemma 2.9b, Llama 3.8b, and Qwen 2.57b.
We should pause on those numbers for a second because they are really important.
The 9b and 8b referred to the parameter count, right?
Exactly. Roughly 7 to 9 billion parameters. In the landscape of AI right now, these are relatively small, highly efficient models.
Yeah, these aren't the massive data center behemoths.
No, they're the kinds of models designed to eventually run locally on your laptop or your phone, rather than requiring a massive server farm.
The fact that Google attempted this on smaller models is a crucial detail we are going to return to later.
Definitely. So let's walk through the actual training ground. How do you teach a language model to do 18th century math?
It is quite an elegant setup. The researchers generated thousands of simulated 5-round conversations.
And the domain they chose was exactly what we started with, recommending flights.
Right. They built a highly controlled simulation with 4 distinct features for the AI to balance: departure time, duration, layovers, and price.
Okay, so behind the scenes of this simulation, Google deployed a symbolic, optimal Bayesian assistant.
And we need to be clear, this was not a neural network.
Right. It was a hard-coded, rigid mathematical engine.
Exactly. It perfectly calculated the shifting probabilities of what the simulated user cared about, strictly using Bayes' theorem.
So every time the simulated user offered feedback like complaining about a layover, this optimal assistant mathematically updated its distribution graph.
And then Google took the LLMs, those smaller models we mentioned, and trained them to explicitly imitate the conversational behavior of this perfect mathematical engine.
This is where the methodology gets really interesting to me. Did they just teach the AI to look at the first prompt and magically guess the final perfect answer?
Well, the researchers actually tested two opposing philosophies of teaching to figure that out.
Okay, what was the first one?
The first was called oracle teaching. In oracle teaching, the model is trained to jump to the perfect final answer as quickly as possible.
So it is penalized for hesitation? It acts like it possesses a crystal ball?
Exactly.
On the surface, that sounds ideal. I mean, I want my AI to give me the right answer immediately.
The problem is that early in a dynamic conversation, the AI fundamentally lacks sufficient information.
Because it can't read my mind.
Right. If a user just says, "Find me a flight," an oracle-trained model is forced to guess blindly.
And when it inevitably guesses wrong.
It doesn't know how to recover because its entire training was based on being instantly correct. It just breaks down.
So what was the alternative?
The second philosophy was Bayesian teaching. Here, the model is explicitly trained to maintain and express uncertainty.
Wow. They trained the AI to be comfortable not knowing the answer right away.
They trained it to understand the value of gathering clues.
Like a real detective.
Exactly. A Bayesian-trained model will intentionally offer a slightly flawed option just to test the waters.
Give me an example of that.
Well, it might offer a cheap flight with a long layover, specifically to see which variable the user attacks first.
Oh, that is so smart. It mathematically narrows down the probability space by observing your rejections.
Yes, it learns by elimination.
That leads directly to the core breakthrough of the paper, a concept they refer to as the invisible probabilistic whiteboard.
This is the part that really takes some mental gymnastics to grasp.
It really does. Because the AI's underlying code, its weights and parameters, is fixed.
Right. It isn't being sent back to Google's cloud to be recompiled every time you type a sentence.
Yet through this Bayesian teaching, the model learns to carry around an invisible whiteboard in its temporary working memory.
As you chat, it is erasing and rewriting the percentages of what you care about entirely on the fly.
What is the actual mechanism for that? How does it store that whiteboard?
The scientific term for this working memory is the model's transient activations.
Transient activations.
Yeah, these are the electrical signals bouncing around the layers during the actual generation of the prompt.
So it's like the active thought process, not the long-term memory.
Exactly. The Bayesian training teaches the model to use those transient activations to structure an internal probability distribution.
It dynamically updates its priors and posteriors entirely within the context window of that specific, isolated conversation.
That is exactly what is happening.
Let's look at the hard data from the Nature paper to see if this invisible whiteboard actually works in practice.
The numbers are pretty staggering.
We established earlier that traditional models hit a wall at about 38% accuracy.
Right, the static parrots.
With Bayesian teaching, the final accuracy of these models pushed to roughly 70%.
Almost double the baseline.
And furthermore, they achieved about 80% agreement with that perfect, hard-coded Bayesian math engine we talked about.
And the trajectory of that improvement is just as important as the final number.
What do you mean by the trajectory?
Well, the accuracy charts in the paper do not show random spikes. The models improve gradually and consistently, round after round.
So it's a smooth curve upward.
Yes. Round 1 is an educated guess. Round 2 refines the distribution. Round 3 narrows it further.
It maps perfectly onto the cognitive process of a human expert narrowing down a client's vague requests.
It really is mimicking human deduction.
Which brings us to the most rigorous and frankly mind-bending part of the entire research stack.
The generalization leap.
Yes. These models were trained only on the simulated flight data, flight times, layovers, and prices.
Right, that was the only data they saw during the fine-tuning.
So logically, you would expect this results in an AI that is exceptionally good at booking flights and nothing else.
But the researchers took these flight-trained models and tested them on entirely different domains.
They asked them to recommend hotels based on completely different variables like amenities and location.
And then they asked them to navigate complex, real-world web shopping scenarios.
And the model suddenly excelled in those untouched domains, too.
It's wild. The scientific term for this phenomenon is zero-shot generalization out of domain.
Zero-shot generalization.
Yeah, it means the model encounters a completely novel task, having zero prior examples in its training data, and successfully applies a learned skill to solve it anyway.
In the web shopping tests, these models, which had only ever seen data about airplane layovers, actually beat specialized models that were fine-tuned directly on web shopping data.
Which is just a massive validation of the technique.
It is the equivalent of teaching someone the underlying abstract strategy of chess-like controlling the center of the board, sacrificing pieces for positional advantage, and then dropping them into a high-stakes poker tournament.
You're watching them totally dominate the table.
Right. They didn't just memorize how the knight moves, they learned the underlying philosophy of probabilistically reading the board.
The models didn't memorize sleight booking. They internalized the abstract mechanism of Bayesian reasoning.
Because probabilistic reasoning is a universal cognitive framework.
Exactly. So the model could instantiate its invisible whiteboard for hotel amenities, for shopping preferences, for literally anything where a user's hidden desires need to be deduced from minimal clues.
And the paper goes out of its way to prove this isn't just a carefully edited tech demo. The rigor here is intense.
Oh, they did not cut any corners.
The testing spans 624 simulated users, plus a cohort of 48 real human testers.
And they ran the experiments across multiple algorithmic seeds to ensure the results weren't statistical flukes.
They maintained incredibly strict baselines for comparison, too.
Right, the p-values across these tests were consistently under 0.001.
For those of us who aren't statisticians, remind us why that matters.
The p-value is the metric scientists use to determine statistical significance. A value under 0.001 means the probability of these massive improvements occurring by mere random chance is less than 1 in 1,000.
So the science is rock solid.
Very solid. The models are demonstrably learning to update beliefs in real time.
So the math works, the science is validated, and we have an AI that acts like a highly competent, adaptive detective.
It's a huge win.
But the obvious question for anyone listening is, why am I still fighting with my phone over a layover today?
Ah, the real world.
Right. How does this breakthrough navigate the friction of the real world to actually reach the consumer?
Well, the path to implementation has distinct hurdles, but also a major tailwind.
Let's start with the good news. What is the tailwind?
The tailwind is Google's concurrent push with a technology called LitterDot.
Right.
It is an execution environment designed specifically for edge devices.
Meaning it optimizes AI models to run directly on local hardware like your smartphone or tablet rather than in the cloud.
Exactly. And LitterT can run these types of models roughly 1.4 times faster.
So because the Bayesian teaching was proven on those 7 to 9 billion parameter models we discussed earlier, they are already compact enough to run on a phone.
Yes. The vision is a localized AI carrying its invisible whiteboard right in your pocket.
Real-time evolving AI that doesn't rely on server lag. That is incredible.
It is. But the sources do detail severe computational bottlenecks before that vision scales to everyone.
What is the biggest bottleneck right now?
The primary hurdle is the compute cost of the training phase itself.
Oh, because running the final model on your phone is highly efficient, but getting it there is hard.
Right. Generating the thousands of optimal Bayesian simulated conversations required to teach the model how to reason in the first place is incredibly compute heavy.
Because it requires running that rigid mathematical engine alongside the neural network for millions of simulated interactions.
Exactly. It is a very expensive training process.
There's also a major scaling question raised in the research.
Yeah. The trillion parameter elephant in the room.
They proved this Bayesian generalization works brilliantly on smaller, focused models. But the broader tech industry is currently obsessed with scaling up to massive trillion-parameter models like Gemini Ultra or GPT-4.
And the paper leaves open a critical question. Will this specific Bayesian teaching technique scale up to a behemoth like that without fracturing or degrading the model's other capabilities?
Like, will it ruin its creative writing or its coding skills if we force it to think like a statistician?
Scaling introduces highly unpredictable variables. We just don't know yet.
But the most unpredictable variable of all, and the final hurdle detailed in the research, is the user.
The human element, always the wild card.
Always. Because an optimal Bayesian model relies on pure, cold math and logical consistency.
And humans are famously inconsistent.
Think about our flight example from the intro. I open the app and type, I want a cheap flight.
So the AI updates its whiteboard. User strongly prioritizes price.
But while we are chatting, I see a targeted ad on my feed featuring a gorgeous first-class lounge with a champagne bar.
Oh no.
I am immediately swayed by emotion and sudden impulse. I type, actually, put me in first class.
You have totally contradicted your initial premise.
I have flipped the board. And the paper explicitly cites this kind of human noise as a profound challenge.
They absolutely do.
Mm.
When they moved from simulated users to the 48 real human testers, they observed that the optimal, mathematically perfect Bayesian engine occasionally fails when faced with our messy contradictions.
Because pure math expects a rational actor.
A rigid mathematical model operates on the assumption that the user has a fixed underlying goal that simply needs to be uncovered through deduction.
It attempts to converge on a perfect posterior probability.
Right. When you suddenly demand a champagne bar after demanding a budget ticket, pure math throws the equivalent of a syntax error. It makes zero sense to the formula.
Interestingly, though, the research noted that the LLMs trained with Bayesian teaching actually showed a slight resilience in these chaotic scenarios compared to the hard-coded math engine.
Yes, they did. Because the language model is inherently a bit fuzzy.
It isn't just pure math, it retains its broad language comprehension, so it can roll with the conversational punches a bit better.
It beautifully bridges the gap between statistical rigor and conversational flexibility,
That this friction highlights the ultimate philosophical challenge for this technology going forward.
finding the balance.
Right. Do we want an AI that mathematically optimizes our requests based on strict deduction? Or do we need an AI that leaves room for human whimsy, impulse, and irrationality?
Finding that exact balance between perfect Bayesian optimization and the messy reality of human behavior is the frontier these researchers are currently navigating.
Which brings us to the ultimate takeaway for your daily life. Let's synthesize this journey.
We are currently witnessing a profound evolutionary leap in artificial intelligence architecture.
We are moving away from the era of static parrots, models that simply spit back text patterns and stubbornly anchor to your first prompt.
Models that reset their understanding every time you clear the chat.
Exactly. And we are entering the era of adaptive partners.
The core value proposition here is an AI that builds an internal, mathematically sound model of your preferences in real time.
It learns your shifting priorities, it updates its probabilities when you issue a correction.
And it fundamentally saves you from the friction of having to repeat your parameters 1,000 times.
So the next time your current AI gets stuck in that infuriating loop, offering you the same terrible itinerary over and over, you now know the exact mechanics of why.
It has hit the 38% wall.
It lacks an invisible, probabilistic whiteboard. But you also know that the Bayesian solution, this dynamic, real-time updating architecture, is fully validated and actively being optimized for edge devices.
The foundational science of teaching an LLM to reason probabilistically is complete. The transition is now purely an engineering and deployment challenge.
But there is a lingering thought to mull over as this technology moves from the research lab to your pocket.
Oh, I like where this is going.
We have spent this deep dive analyzing how this invisible probabilistic whiteboard allows the AI to track your subtle clues and deduce your hidden preferences.
Right, narrowing down the variables to find out what you really want.
If these edge device models are getting this incredibly sophisticated at calculating the mathematical probabilities of our choices, what happens on the day your AI deduces a profound behavioral pattern about you before you have even realized it about yourself?
Oh, wow. That is a heavy question.
If an AI can map your preferences more accurately than your own internal monologue, are we actually ready to be understood that perfectly?
That really is the ultimate threshold of adaptive technology. The exact moment the tool can predict the user's trajectory better than the user can.
Something to think about the next time you type a simple request into your phone. Thank you for joining us on this deep dive into the evolving mind of AI. Keep staying curious, keep asking the hard questions, and keep exploring the data. We will catch you next time.